What if you could unlock the deepest secrets of how stars generate energy, and then find yourself helping create the most powerful weapons humanity has ever known, and then dedicate your life to controlling them? That's the kind of extraordinary journey we're taking a deep dive into today. We're focusing on a true titan of 20th century physics, Hans Bethe. Okay, let's unpack this a bit. We're talking about Hans Bethe, a German-American physicist. His intellectual reach was just, well, incredible. Spanned everything from nuclear physics, astrophysics,
Hmm.
quantum electrodynamics, even solid-state physics. Now, he's maybe most famous for his Nobel Prize in Physics, right,
Yeah.
back in 67, for figuring out how stars make energy stellar nucleosynthesis. But his story, it goes so much further than just that one achievement.
Exactly. And our mission today really is to pull out the most important nuggets of knowledge, the key insights from what we know about him. We want to give you a shortcut, basically, to being well informed about Bethe's huge scientific contributions, but also his really deep ethical engagement later on. We'll try to connect the dots, between his groundbreaking theories and his advocacy work, not just what he did, but why it still resonates, why it matters today.
And his career was just astounding. It spanned nearly 70 years. Think about that for a second. 70 years. He was one of the very few scientists, maybe the only one, to publish a major paper in his field every single decade of his working life. So yeah, you'll hear about his genius, definitely, but also his surprising sense of humor, apparently, and this unwavering conscience he developed, especially when faced with unimaginable power. So let's start at the beginning, his early life. He was born in Strasbourg, which back then was part of the German Empire, July 1906. Came from a scientifically minded family, which probably helped. He started off studying chemistry, actually, at the University of Frankfurt, but he quickly realized, nope, that wasn't it. His real passion was theoretical physics. So off he went to the University of Munich to study under the legendary Arnold Sommerfeld.
Right. And what's fascinating here is how early you could see his analytical power. His PhD work under Sommerfeld was on electron diffraction in crystals. I mean, that sounds technical, but it's really fundamental stuff about how matter interacts with particles. Showed he really grasped complex quantum mechanics early on. And there's that great anecdote, isn't there, about Wolfgang Pauli?
Oh, yeah, the backhanded compliment.
Exactly. Pauli read his thesis and apparently said something like, "After Sommerfeld's tales about you, I had expected much better."
Ouch.
But Bethe, ever the pragmatist, apparently took it as a compliment. It said it showed the high expectations people had, which, he consistently met.
He certainly did. Even really early back in Europe, he made some huge breakthroughs. There's the Bethe formula, which basically simplified how you calculate what happens when fast particles like electrons go through stuff matter.
Which sounds abstract, but it's crucial for so many things. Radiation shielding, medical tech. Bethe himself thought it was his best paper.
Right. And then there's the Bethe and ansatz.
Yeah.
Well, you explain that one.
Okay, the Bethe ansatz. It's a really clever mathematical method. It lets you find exact solutions for certain types of quantum systems, these one-dimensional many-body problems, which are usually incredibly hard to solve. It's sort of opened a door into understanding systems where particles interact really strongly. Super important for things like condensed matter physics later on.
And he had a sense of humor, too, didn't he? That hoax paper.
Oh, yeah. He co-wrote this spoof paper, basically making fun of some of the wilder, more speculative physics theories floating around at the time, like Arthur Eddington trying to derive fundamental constants purely from theory. They actually had to apologize afterwards.
But then things took a really dark turn.
Yeah, abruptly. 1933. Despite being raised Protestant, Bethe was kicked out of his job at the University of Tübingen. Why? Because his mother had a Jewish background. This is the Nazis' so-called law for the restoration of the professional civil service.
Just off.
It was. And if we connect this to the bigger picture, this wasn't just Bethe. It was part of this massive brain drain from Europe. So many brilliant scientists had to flee. It fundamentally changed the scientific landscape, especially boosting science in the U.S.
So he left Germany, went to England first.
Worked with Rudolf Peierls there, got him interested in nuclear physics. And then Cornell University offered him a position.
So February 1935, Bethe lands in the United States, joins the faculty at Cornell. And this wasn't just, filling a spot. Cornell actively wanted him to help build up their physics department, especially in nuclear research.
And he jumped right in. He co-authored this series of 3 big review articles with Robert Batcher and Stanley Livingston. They basically summarized everything known about nuclear physics at the time. People call it Bethe's Bible.
Bethe's Bible. Love that.
Yeah, it was the standard textbook pretty much for years.
Okay, so he's at Cornell, establishing himself, but there's this huge question hanging over physics.
Right. How do stars actually work? How does our sun produce all that energy? This was the big topic at the Fourth Washington Conference on Theoretical Physics, March 1938.
And Bethe almost didn't go, right?
Apparently not. Didn't grab him initially, but Edward Teller talked him into it. Good thing he did.
Because here's where it gets really interesting. This leads straight to his Nobel Prize. At that conference, he worked with Charles Critchfield, and they developed the proton-proton chain reaction.
Which explains how stars, like our sun, the smaller ones, fuse hydrogen into helium. That's their main energy source.
But he didn't stop there. He then, on his own, figured out the CNO cycle, carbon, nitrogen, oxygen.
Which is the dominant process in heavier, hotter stars. Another way to fuse hydrogen, but much more powerful.
And the story behind that paper, the furniture.
Oh, it was fantastic.
Yeah.
His mother had emigrated from Nazi Germany, but her furniture was stuck in customs. He needed $250 to get it out. So he saw this prize being offered by the New York Academy of Sciences, $500. He actually pulled his CNO cycle paper from Fiscal Review, submitted it for the prize, won it, got the furniture.
Amazing. Talk about pressure.
And then the paper got published in March 39. And yeah, decades later, 1967, that work won him the Nobel.
Yeah.
It really shows how science and, well, life just intertwine sometimes.
And the validation came much, much later, too.
Oh, absolutely. Decades later. In 2002, Bethe was 96 years old. He sent this handwritten note to John Bacall. Bacall's team had made these solar neutrino observations that finally confirmed the CNO cycle accounts for about 7% of our sun's energy, too, not just heavier stars.
Wow, at 96.
Yeah. And that note apparently helped push things along for Raymond Davis Jr. getting his share of the Nobel that year for neutrino work. Bethe really laid the foundation, and he lived to see it confirmed in incredible detail.
Okay, so the world is heading towards war. Bethe, having fled the Nazis himself, obviously wanted to help the Allied effort. He becomes a U.S. citizen in March 1941, and his focus shifts dramatically.
Yeah, he started doing war-related work, things like shock waves, armor penetration, important stuff. But the big one, of course, was Los Alamos, the Manhattan Project. He was asked to lead the theoretical division, the T division.
The secret project to build the atomic bomb, and he's leading the theory group.
His role there was just
Yeah.
absolutely essential. You can't overstate it. He calculated the critical mass for uranium-235, how efficient the bomb would be, fundamental stuff. He developed the theory behind implosion, which was totally necessary for the plutonium bomb, the one they tested at Trinity and used at Nagasaki, Fat Man.
And he worked with Feynman on the yield calculations.
He collaborated with Richard Feynman on the formulas to predict how powerful the explosion would be.
And we have to talk about that. That terrifying possibility Teller raised.
Ah, the atmospheric ignition scenario.
The fear that setting off an atomic bomb could actually set the atmosphere on fire, burning up all the nitrogen, a global catastrophe.
It sounds like science fiction, but they had to take it seriously. Bethe, working with Emil Konopinski, crunched the numbers. They showed pretty definitively that it was virtually impossible. Couldn't happen.
Imagine the relief, but also just calculating that, the weight of it.
Absolutely.
Yeah.
And this whole period, it clearly marks the beginning of the ethical struggles for Bethe and many others.
Right.
Remember that quote from the Trinity test, July 45, when the bomb actually worked, validating all their theoretical work?
I am not a philosopher.
Exactly. You connect that to the bigger picture. It's the start of this profound reckoning with what they'd created.
And that reckoning definitely continued after the war, didn't it, with the hydrogen bomb?
It got complicated. He initially argued against a crash program to build the H-bomb. He thought it was a terrible idea.
But he ended up joining the project anyway.
He did. After President Truman announced the U.S. would pursue it, and the Korean War started, he felt he had to. Partly, he said later, he hoped he could prove it couldn't be built.
Which obviously wasn't the case. He called himself the midwife of the H-bomb.
Yeah, with Stanislaw Ulam as the father, he had the key idea, and Edward Teller as the mother. That relationship with Teller really fractured, though.
Especially during the Oppenheimer security hearing in '54.
Right. Bethe strongly defended Oppenheimer. He argued that the breakthrough Teller-Ulam design for the H-bomb wasn't delayed by Oppenheimer's earlier doubts. It was just a matter of hitting on the right idea, almost serendipitously. Big split there.
So, the war's over, the Cold War is ramping up. Bethe goes back to Cornell. But he doesn't stop doing science, not by a long shot. He dives right back into fundamental physics.
Yeah, and tackles this major puzzle, the Lamb shift.
Explain that one. It sounds subtle.
It was subtle, but hugely important. Willis Lamb and Robert Rutherford discovered that one of the energy levels in hydrogen atoms was slightly off from what Dirac's theory predicted. Now, Dirac's theory was amazing, but this tiny discrepancy showed something was missing. Existing quantum electrodynamics, QED, was giving infinite answers for certain calculations, like the electron's self-energy. It was a real crisis.
Okay, so QED is in trouble.
Yeah.
And Beth figures it out.
He does. And the way he did it is just classic Bethe. Apparently, he did the key calculation on a train ride, New York to Schenectady.
On a train, seriously.
That's the story. He realized the main effect was non-relativistic, which made the math way simpler. His paper came out August 47. It was only 3 pages long, 12 equations. But it got a value for the shift, 2040 megahertz, incredibly close to what Lamb measured.
Wow.
It showed QED wasn't fundamentally wrong, just needed refinement renormalization. Feynman called it the most important discovery in the history of QED. Dirac said it was the most important calculation for decades. High praise.
And his curiosity didn't stop there. He went back to stars later on.
Absolutely. He started using the tools of nuclear physics to look at extreme objects like neutron stars and supernovae. He had this knack for taking incredibly complex, messy astrophysical events and boiling them down to solvable equations, figuring out the physics of stellar collapse, things like that.
And then much later, neutrinos, he got involved in the solar neutrino problem.
Yeah, when he was 85. This was a huge puzzle for decades. We knew the sun should produce a certain number of neutrinos from nuclear fusion.
But experiments on Earth were only detecting about a third of them. Where were the rest?
Exactly. Bethe played a key role in understanding the mechanism now called the MSW effect, where electron neutrinos produced in the sun actually change flavor on their way to Earth, turning into muon or tau neutrinos that the early experiments couldn't detect.
So the neutrinos weren't missing, they were transforming.
Precisely. And the huge implication was that neutrinos must have mass, which was not part of the original standard model of particle physics.
So his work forced a rethink of fundamental physics again.
Right. It shows how science sometimes has to question its own foundations.
Yeah.
And he got confirmation from the Sudbury Neutrino Observatory, SNO, when he was nearly 95. Just amazing longevity.
Even into his 90s, still going, he worked on LIGO, the Gravitational Wave Observatory.
Incredible, isn't it? At age 90, he was collaborating with Kip Thorne, doing calculations related to the mergers of neutron stars and black holes, the very things LIGO was built to detect.
It really drives home that point about him publishing major work every decade for nearly 70 years. Unbelievable sustained contribution.
But beyond the pure science, which is staggering, he also became this incredibly important voice on, well, the implications of science. Arms control, responsible use of technology. Like in 1968, he worked with Richard Garwin, an IBM physicist, and they wrote this devastating critique of the anti-ballistic missile systems being proposed back then. They argued, with very solid technical reasoning, that these hugely expensive systems could be easily fooled by simple decoys. His technical authority gave his arguments enormous weight.
And he was key in the push for the Partial Test Ban Treaty in '63, right?
Absolutely instrumental. One of the leading scientific voices arguing for banning nuclear tests in the atmosphere, underwater, and in space. A huge step for environmental safety and slowing the arms race.
He also defended nuclear energy, though, even after Chernobyl.
He did. He looked at Chernobyl and concluded it wasn't an indictment of nuclear power itself, but rather a result of a terrible reactor design, masked of human error and flaws in the Soviet system. He saw nuclear power as a necessity, not merely an option. He believed we needed it, despite the risks, which he argued could be managed with better designs and oversight.
And one of his last big public statements, that open letter in 1995.
Yeah, that was powerful. He was 88. He wrote this letter urging all scientists everywhere to cease and desist from working on nuclear weapons, developing them, manufacturing them, anything.
Coming from him, head of the T Division at Los Alamos, that carried immense moral weight.
It really did. If you connect this to the broader picture, like historian Greg Herkin said, Bethe really took on that role of the scientist of conscience, similar to Oppenheimer in some ways. He had this unique combination of unparalleled technical expertise and deep moral thinking. It made people listen when he spoke about these critical issues.
So there you have it, a glimpse, really, into the incredible life of Hans Bethe, the physicist who figured out how stars shine, helped create the atomic age, and then spent decades wrestling with its consequences and trying to guide humanity towards responsibility.
He was just a giant. Freeman Dyson, one of his PhD students, called him the supreme problem solver of the 20th century. And cosmologist Edward Kolb called him the last of the old masters of physics. His legacy isn't just the theories or the Nobel. It's in the students he mentored, the countless awards, the institutions named after him, like the Hans Bethe House at Cornell, the APS Hans Bethe Prize.
So what does this all mean? What's the takeaway for you listening? Hans Bethe wasn't just, a brilliant scientist locked away in an ivory tower. He lived the power and the heavy responsibility that comes with scientific knowledge. His journey, I think, it really challenges all of us to think about our own roles in a world that's so profoundly shaped by science and technology.
And maybe consider this final thought. Bethe himself confessed later in life that he wished he'd been a more consistent idealist regarding his decision to work on the H-bomb. So what is his life, his choices, his reflections? What does it teach you about that constant, difficult tension? The tension between scientific ambition, your own personal convictions, and the often urgent demands of the world around us, especially when the stakes are as high as the future of humanity itself.